Welcome to Natural Habitat Adventures Daily Dose of Nature. Today's topic, the largest mass extinction on Earth, insight from the Permian period, presented by NatHab Expedition Leader Eleanor Edye. I'm your host, Rob Mess. Thank you so much for joining us here today. Over to you, Eleanor.
Hi, everybody, and thanks, Rob, as always, for the introduction. As Rob said, my name is Eleanor, and I'm one of our expedition leaders here at Natural Habitat Adventures. I am based mainly in Canada, but work elsewhere as well. And today we are here to talk about the ever cheerful subject of mass extinctions. If you've been watching some of the webinars in the past, you may have caught a few of the other mass extinctions that we've covered so far. But today we have come not to the most recent, not the earliest, but the biggest, the most destructive, kind of the ultimate mass extinction to which the world almost didn't come back from. So today we are going to be talking through the end Permian extinction, kind of lessons from this time, what we can carry as knowledge into the times that we're in right now. And I'd like to, send out a special thank you to everybody who's tuned in today, because this is not a cheerful webinar about, you know, koala bears or polar bear cubs. We have some hard lessons ahead of us in the next hour or so. So I find mass extinctions inherently interesting. I've always found big picture and old picture things to be something that we can always take a lesson from. And I'm so glad that those of you who are here today have also kind of want to learn more about lessons the past can teach us. So as we've kind of gone through our exploration of mass extinctions, we've been looking at kind of the way the world used to be and what extinctions kind of have brought out into the other side, so that we may lose things in the extinction, but then gain things in the times to come as as biodiversity comes back after a mass extinction event. Today we'll certainly talk about the living beings that existed before this extinction event and those who are still present afterwards. But what I'm really going to be talking about today is looking at the Permian extinction as a window into the past and into ways that our planet system functions. So extinction events usually occur because of one or more triggers that cause a massive change in the environment. So as we look at these triggers, what were they? What were the outcomes that happened from these triggers, right? Extinctions are not random events. They happen because of these perturbations within the Earth system. And these changes are usually to do with climate, and we're going to see this today as well. So let's take a broad picture look here at what we're talking about. So we can divide the geological ages of the Earth into different periods. These periods were kind of marked by periods of overall sameness. We had similar fauna, we had similar flora, and we had similar climatic conditions. So the Permian period is one of these periods, and it happened between 299 to 251 million years ago. And the end of the Permian was the biggest extinction event that we have ever had happen on this planet. It also marks the end of a major kind of time frame called the Paleozoic. The Paleozoic means old life or ancient life. So as we moved through the end of the Permian, we moved out of the time of old life organisms and into the time of the Mesozoic, the middle life organisms. As we've been saying, the end Permian was the most extensive and extreme extinction event ever recorded in the planetary record through paleontological records. At this time, between 90 to 95 or even upwards of 97% of all species that lived in the oceans and seas became extinct. About 70% of all land species, both plant and animal, became extinct. It is also the only time that we have really ever had a mass extinction that has affected insects. And as geologists like to give names to things, we all like good names. The end Permian extinction is also colloquially known as the Great Dying. So all of this is going to set us up for what we're talking about here. Now, mass extinctions in general, just to really quickly cover some information that we touched on in previous webinars, but to bring us all kind of into the same alignment here. When we talk about these mass extinctions, we're talking about a time when the extinction rate was greatly higher than what is normal. Throughout time, we've always had speciation happening with new species coming into being, and we've always had extinctions. And at a time of mass extinction, we have fewer species evolving and more species going extinct, like well outside what would be considered the normal background rate. And when paleontologists first started looking at biodiversity over time, they were able to identify 5 big time events that occurred in the Earth history, often now known as the Big 5 mass extinctions. We now know that these are likely not the only mass extinctions. There's debate around timings and which ones were the biggest ones, but there's one thing that we do all agree on, and that is that the Permian extinction happened. There's no question about that, and there's no question that it was the biggest one to have ever occurred. This infographic we have here kind of just takes us from modern day up at the top down to ancient days at the bottom here. And this today will mark the 4th mass extinction that I have talked about on our Daily Dose series here. So we started by talking about the Great Oxygenation Event, which was probably the most catastrophic mass extinction event in that it changed the very chemistry of life on this planet. But everything that's come since has really existed with that same chemical background. Almost all of us are oxygen using organisms, and we've talked about mass extinctions at the end of the Ordovician periods, at the end of the Devonian period, the age of fishes, and now we're talking about the gigantic extinction as marked here at the end of the Permian. So something to be aware of with this scale here, this is not a scale like that's true to scale. If you look up at the top, the Cenozoic, that is the modern life, that's only since the time of the dinosaurs, so only the last 65 million years or so. And the time scale compresses as we go back in time here. So we're still looking pretty far back in time. 250 or so million years is pretty far back indeed, but not nearly as far as we were talking about the Great Oxygenation Crisis. So let's talk about what the world was like at this point, starting with the climate and the geography. So here we have there's 2 curves that are shown on this graph here. The blue line up above is the temperature averages, and these are tracked through, obviously, like we didn't have temperature probes that we can go back and check what the temperature was 250 million years ago. We're using a lot of proxy measurements for these that we can talk about later if there are any questions, or might do a webinar just on those. But we have proxy measurements like checking various chemical signatures and rocks and such that give us a really good indication of what the temperature was at various times. So our last extinction event that we talked about was the Devonian in this period here. That was a time of mass cooling. We had the temperature dropping. We had also that bottom line there, the carbon curve. We had the amount of carbon dioxide in the atmosphere dropping as well. And as we talked about in the Devonian, this marks kind of the first forests on the land. And the thinking around why the carbon dioxide content drops so thoroughly at this point was that these new trees were actually removing a lot of carbon dioxide from the atmosphere. And with this, the temperature dropped as well. We are today going to be talking about the Permian. Here we go. So the Permian is a time where we are moving from a cold Paleozoic icehouse Earth when temperatures were very cold, colder than today, and much colder than they had been before that. And then moving into a time of very, very high temperatures, so higher and much higher than today. We also see here an uptick in the amount of carbon dioxide in the atmosphere as well. So the carbon dioxide measurements here are not an absolute measurement. They're just showing us relative to the amount of carbon dioxide that we have today. That hatched line along the bottom there represents the amount of CO2 currently in our atmosphere, and then orders of magnitude more above that, so multipliers on that green line. So in short, the Permian was a time of change. We went from cold to hot. We went from not too much carbon dioxide to a lot of carbon dioxide. What did the planet look like? Well, maybe you've been waiting for this moment that we can finally talk about Pangaea. Pangaea, or the supercontinent of Pangaea, is when all of the Earth's terrestrial tectonic plates came together into one big mass, basically. So we had North America and South America and Asia and Europe and Antarctica and Australia all kind of butted up against each other here, spanning from pretty high latitudes to pretty high latitudes. So it didn't quite reach all the way up to the North Pole, but it did go over the South Pole. This growing together of Pangaea happened throughout the Permian. So at the beginning of the Permian, this had not fully closed up as a single continent, but then by the late Permian, this is what we were looking at here. So one big continent with some seas, and then a lot of ocean, or panthalassic ocean, around the supercontinent of Pangaea. Now, if we think about kind of what this means for organisms trying to survive in this landscape, there's been other times we've talked about, for example, in the Ordovician, where we had a lot of coastline. We had a lot of continental breakup. We had a lot of shallow seas. We had a lot of reef-building organisms at that time, for example. Now here, with all of our continents jammed in together, we don't have as much coastline. We don't have as many shallow seas. Certainly not none, right? There were some island archipelagos. There were certainly shallow seas, as you can see here with the lighter blue shown on the map. So there were still coastal organisms, there were corals, but not nearly as much as what we'd seen in previous times when the world was really dominated by those shallow sea organisms. The other thing that we're seeing here, well, one of the other things, is that this continent spans huge latitudes, like all the way from the North Pole almost to the South Pole. This would have a big effect on the way ocean circulation worked. It would be very different than today. So circulation would still have happened, right? Our warm water from the equator is going to be pulled into those colder waters of the polar regions, but it would look very different than today, and we can't say, but we suspect that it was a less efficient movement of heat. The other thing that's going to happen on the land itself is that we have, in essence, one giant continent. And if we think about our big continents today, like North America, like Africa, like even Siberia, like Asia, even though it's over a higher latitude region, when we think about the middles of those continents, those are areas that tend to be very, very seasonal. So they are hot and then they are cold, and that they are also very, very dry. If you picture the middle of most continents, that is usually the driest part of that continent, simply because the moisture is not going to make it all the way from the sea up in, like, it's going to fall out of the clouds as rain before it reaches the middle of the continent. So we have massive deserts developing across Pangaea in the middle of these supercontinental regions here. So as we kind of continue on here, we're going to be looking at the organisms that lived at this time. And this is going to be a little different than previous webinars, where we're going to go through some of these fairly quickly as we talk about what the world was like before this mass extinction. And in the past, I've talked about, what lived, what died, what made it through. The difference here is that, nearly everything died. Nearly everything was gone. Not just species, but whole genera, and families. Having a species loss of over 95% in the oceans More than 50% of families were lost. So an incredible, incredible loss of biodiversity through this time. Oh, before we talk about what was there, here's just that temperature profile I was talking about here. So it was hot. It was hot and dry on the continent, the supercontinent. And it was warmer than it is today all across the board. So it was warmer on land, it was warmer in water, and it was especially warmer in the polar regions. So we saw temperatures at those polar regions, like towards the North Pole and the South Pole, between 10 and 30 degrees Celsius warmer than today, and that would be around 20 to 55 degrees Fahrenheit warmer than today. So now let's go on and look at what was living in these habitats before these massive changes started to happen. All right, we'll start with the oceans. So if you recall back to our last mass extinction, because we have had multiples of these, right? This just being the most kind of the worst of all of them. In the Devonian mass extinction, we lost our bony fishes, we lost a bunch of corals, we lost a bunch of diversity within the oceans, but we've had time since the Devonian. We've had, almost 80 million years since this last mass extinction. Biodiversity has recovered. We had sharks, we had fish. We call it now primitive, but we just mean that as meaning old life. We don't have a lot of these organisms anymore. These represent the oldest type of life on Earth. So there were reefs. The type of reefs that we had were different than what we had today because all these reef builders died. We had sea scorpions, we had all sorts of wonderful things here, and we had trilobites. So on the left-hand side there, that is a fossil of a trilobite. The trilobites are really kind of the flag holders, the animals that stand out as a marker of the Paleozoic, of that old lifetime. They had managed to survive every mass extinction until this point. Spoiler alert here, they did not make it through. They were one of the earliest known groups of arthropods, that same group that has gone on to give us a lot of organisms now. In the middle there is another fossil. This one's of a blastoid, which is a type of echinoderm. They are related to the sea lilies as well as to organisms like the starfish of today. They had a calcium carbonate shell and were attached to the seafloor by a little stalk. So they were filter feeders, similar to what sea lilies do today. And then on the right-hand side, you've got a sea scorpion, a Eurypterid. They were a group of arthropods as well, and they were pretty big. They were a major predator of this time, especially of the freshwater areas. We had forams, which are the kind of a smaller word for foraminifera. They're interesting little organisms that we use a lot in our look back at histories because they are often found in the ocean. They're actually right? They're small organisms overall. They catch teeny little bits of food. They build a little shell around themselves, and they're found throughout the ocean, throughout ocean waters. They build a calcium carbonate shell there. We had ammonoids, which are ancient cephalopods related to today's squids. We had the spiny sharks, as shown on the upper right there. These are not a group that we have today, but spiny sharks, they're known as spiny sharks not because they're really related to today's sharks, but because they filled that shark type of niche at this time. And they had bony spines on all the fins, which did fossilize really well, which is where that common name spiny sharks comes from. And we had corals, we had tabulate, and we had rugose corals, which are types of corals that we've seen at different older times of the past here. And there certainly were fish. We lost a lot of fish in those Devonian extinctions, but they did rediversify and come through this time. Of course, we still have fish today. In terms of what made it through this time, we've already given it away. Not that much did. Our single-celled forams did make it through. We still have foraminifera today. Interestingly enough, the ammonoids made it through. We still have cephalopods in today's oceans, But we not just these organisms lost, right? We lost 95% of the biodiversity in the seas. And on top of that loss of biodiversity, if you can imagine losing 95% of, not just the fish, not just the nautiloids, not just the trilobites, but 95% of the bacteria, 95% of the algae, 95% of the kelp, 95% of everything, along with whole groups being lost, you can easily see that there was a complete destruction of the ocean ecosystem as a whole. The ecosystems that made up the well-developed, trophic levels and predators and primary producers, everything collapsed, leaving us with just a very, very small group of organisms left. You can still go see Permian reefs. There are some that are above ground, and you can kind of look at that division between the Permian and what came after the Triassic. But all that we know of today of what's left of Permian reefs are from the geological record. Every species of coral that existed at this time did not make it through. Corals had to re-evolve. Corals have evolved several times, but the corals that we have today are not really closely related to the corals that existed then. All of the ones that we had in the Permian died. This here is a limestone peak in Texas. It's known as El Capitan. Perhaps you've seen it before, but it is a remnant of a Permian reef. So it was made up of corals and sponges and brachiopods and bryozoans that were all cemented together by encrusting algae, just like today's reefs. And they would have also had photosynthetic symbionts in them, just like today's reefs. So when temperatures started to increase in the Permian, this particular mountain, where that reef was located, the seas dried up. It was encrusted with things like salts and various other minerals, and it now sits above ground today as kind of a standing reminder of what was here at that time. When you look at it here, what replaced the reefs after they were all gone was basically piles of slime. Small things like bacterial mats were able to grow on top of dead reefs. And that was kind of the ocean after the Permian mass extinction, was an ocean, basically a dead ocean of slime. So that's the oceans. Well, we took them out. Let's talk about the land. The Permian was a time of immense forestation. Not everywhere, but certainly not in those desert areas like we were talking about. But there was a big radiation of large, like big plants, diverse forests, especially in the higher latitudes where it was a bit cooler. At the beginning of the Permian, we mostly had organisms like lycopods and horsetails, ancient calamites, so mostly spore-bearing plants. They did not yet produce seeds. Seeds had not yet really evolved at this point. But as we progressed through the Permian and things started to heat up and things started to dry out, spore-producing plants did not do nearly as well. If you think about what a spore needs, spores are very fragile ways to reproduce because you're really counting on that single cell landing somewhere that it can grow with enough nutrients and enough moisture. And if you're living somewhere now that's really, really seasonal with lots of hot and cold and dry and wet, having spores is not optimal. So instead, what we see replacing a lot of these bigger spore-bearing forest types are now some of our first big seed plants. Things like gymnosperms, which are the kind of the ancient precursor to plants that we have today, like pines and spruce and junipers. Also plants like cycads, if you've ever seen like a cycad plant or you grow them, that they come from this period of time. And ginkgos. Today we only have one species of ginkgo that is still living on the planet, but at this time there were many, many, probably hundreds of species of ginkgo that could be found throughout the Permian. So when we think about our conifers, our gymnosperms, those seed-bearing plants, this was a really smart evolutionary adaptation, because what a seed does that's different than having a spore is that when you send a seed out into the world, you're sending it with a little care package of everything that it needs, right? So a seed usually has an embryo growing within it, so it's already got both genetic copies from its parents. It's got a full component of its genetic material and it's ready to go. And it usually gets sent with some extra calories on board as well. So this is why humans like to eat seeds and nuts. We get all those calories and we get to eat them. But the biological purpose of having a seed is that then your offspring gets to sit inside, a seed case and not start to grow until conditions are right. And then when it starts to grow, it's got that package of nutrients and calories with it to help it get a head start. So this was this pressure of having these extreme seasonal environments, having these hot and cold, dry and wet times, is what really pushed seed plants forward as an evolutionary strategy throughout the Permian here. This image that we see here is probably one of the most famous species from this time. This is the Glossopteris plant. It is we used it to recognize back when we didn't have as much information about how these continents fit together. This helped us piece together, because there were so many fossilized examples of Glossopteris, how the continents fit together at the time of Pangea. In terms of what made it through for plants through that mass extinction, it was less about, which major groupings didn't make it through. Certainly there were some families of plants that died, but mostly what didn't make it through was the ecosystems, right? The forests died. Many of those large plants disappeared, right? Some bigger groups were never seen again, some of those families. Most of the families suffered enormous losses. So we saw losses at the ecosystem level, at the continental level. We only had 70% loss of these species. It did better off than the ocean did, but we had, like I said, just real breakdown of the ecosystems, to the point that so many plants died, like basically everything died, that we can track in the lithography, looking back at the layers of rocks at this time, the presence of massive blooms of bacteria in the soil and in the lakes nearby where these forests used to be, because of the die-off of plants releasing all these nutrients and contributing to massive soil erosion. So just, again, massive, massive destruction. One of the things that did make it through, which I just wanted to point out there, things did survive. This is a podocarpus, also known as a plum pine, still found today in Australia. So we still have some of those ancient plants that live with us in very, very specific areas, but most things are really, really reduced in number from this time. Okay. Oh, before we get to land animals, let's talk about what we're going to see on the land as well. So with the land animals, we have had a lot of evolution happening. So our last mass extinction, we said those tetrapods, those four-legged organisms, had really just made it onto land. They weren't doing much, but now we have a big, big radiation of land animals happening. And this is one of my favorite animals from this era. This is Dimetrodon, often kind of lumped in with the dinosaurs, but this is not actually a dinosaur at all. He predates dinosaurs. So all of those kind of lungfish and those bony fish that have been sort of crawling onto land in that time of the Devonian have now made it. They are successful, they are on land, and they have split into two major groups of reptiles. So these are all animals that are laying eggs that can survive on the dry land. One of those groups of reptiles were the ones that would go on to give rise to the crocodiles, the snakes, the turtles, the lizards, the dinosaurs, the birds. And then the other group would go on to eventually become mammals. And that group is the one that Dimetrodon here belongs to. It is a group called the synapsids, right? And they eventually, like, they were some of the ones who laid eggs specifically built to survive on land, just like our other group of animals that we're talking about here. But the sauropsids were the snakes, crocs, turtles, dinosaurs, all those guys. And here we have the synapsids, of which Dimetrodon is one. Now, all of our kind of synapsids and sauropsids that existed through this time, their main evolutionary driver was trying to exist with this big change happening in the forests. So going from generally pretty easy to eat plants to these really hard to eat things. You don't see many animals today browsing on a pine tree because that's not a very palatable type of food. But this is what the land animals of the Permian had to contend with. They had to be able to eat these new tough plants. So the synapsids kind of continued to evolve and gave us now, this is a type of synapsid, but it's a specific type called a therapsid. And the therapsids are the ones who went on to give rise to mammals later on. And these types of organisms here, like this guy here, these are the land animals, the quadrupeds that were kind of the last animals standing before that major apocalypse hit. So there's one. Here's one of the predatory ones. This is Gorgonopsida, named after the Gorgon mythological beast. You can see how large they were relative to the size of a human here, and they would have been, for example, preying on some of those other organisms that we saw. And again, almost all of our land dwellers, most of them also died. Not much made it through the Permian from the synapsids. What did survive was usually what was pretty small. This is an organism called a cynodont. Cynodonts were what survived. They laid eggs. They might have had some hair. They were kind of dog-like in size, herbivores and carnivores with big old plant grinding molars. And I'll kind of point out the biggest one that survived in a little while here. There were animals in the sky. The first known gliding vertebrate was this guy here, and I'm going to probably butcher the name, but I'm going to try. It's Vigeltosaurus. Vigeltosaurus, an extinct animal here. One of the sauropsids. So this would have been an ancestor of the dinosaur and the crocodile lineage here. But four-legged beasts flying in the sky were not the only things that we had in the sky. This is really a time of major insect diversification as well. So insects appeared and became abundant in the period just before the Permian, which is called the Carboniferous, and they experienced a huge diversification during the early Permian. So we had things like true bugs, like the ancestors of cicadas and grasshoppers and bedbugs appear at this time. We had the ancestors of damselflies and dragonflies. We had the first beetles. We had the winged insects starting to appear, like the insects that go through a metamorphosis. So the ancestors of the butterflies and the moths. The largest insect ever known to have inhabited the earth existed at this time, and it was an ancestor of a dragonfly. So this was a big, big time for insects. And like I mentioned before, this is the only time that we've seen a mass extinction impact insects. Every other mass extinction that's occurred since their kind of diversification, they have walked on through with no problems. Okay, so that's what was here, and that's all the things that died. Let's talk about how on earth this all happened, because we're going to talk through this, and we're then going to start getting into what this teaches us for today and our future. So I'm going to tell you kind of what the world was like at the end of the Permian, and it's going to sound pretty darn terrible. So we had global heating. We talked about how, our carbon dioxide content in the atmosphere was rising. Therefore, our Atmospheric heat was rising as well. Carbon dioxide traps heat within the atmosphere. So when we have more CO2, we're going to have more heat throughout our planetary system as well. We know that it was really hot for a lot of different reasons. One of those reasons is that all of those like inland seas, all of those coastal regions completely dried up. And most of the salt that we use today, like for salting our roads and industrial salt, comes from this time. If you live somewhere where they salt the roads, you are driving on the wasted, continental marginal sea that dried up and where everything died at the end of the Permian. It was so hot that everything just evaporated away, leaving the salt deposits behind. And you can see just looking at this map here how extensive they are around today's Earth. So big areas of salt basins left from this period of global heating. There was acid rain. So the rain itself was toxic and acidic and had lots of impacts that we're going to talk about. The oceans became acidic. The oceans were also anoxic, meaning that they did not have any available oxygen for the organisms living there in the water. There were widespread wildfires and destructions of the ozone layer. So two things there. So the ozone layer was impacted by the things that we're going to talk about here. And there were wildfires spreading through all of these forested regions. And the atmosphere itself became toxic because of a release of toxic gases. Now, when we look at these conditions, we're going to say, what on earth could have caused all these things, right? And what causes all these things, we use the terminology extinction drivers, because like we said, extinctions don't just happen. There are things that push them along. And usually without these drivers, the world kind of relocates itself back to its middle and continues on as normal. So we had to have at least one thing, and usually there's more than one thing, that pushes animals and pushes the world itself to the brink of survivability here. One of the early theories around how the world got so toxic was looking at maybe there was a meteor impact similar to the one that ended the dinosaur era. But we've never found anything similar to that. So we've never found a suitable crater. So instead, we're going to talk about what are currently considered to be the most likely culprits and causes for these extinction conditions. The biggest driver, and one that you may have already heard of, is something called the Siberian traps. They're called Siberian traps because they are in Siberia, and the geological term traps refers to a word that means like a stepped hill. So these are big stepped hills made of basalt. So basalt, if you've ever been to Iceland or been to anywhere that's had volcanic activity, it's a very common volcanic type of outflow rock. These Siberian traps here, if you look at the map, cover an enormous area. So huge, like nothing we've seen ever before on this kind of scale for eruptions. They continued for roughly 2 million years. They cover 3 million square miles of Earth, so about 7 million square kilometers of lava. And to give you some perspective on how much lava this is, if we put this lava on the lower 48 United States, it would cover that entire mass of land half a mile deep. If you've heard about, the super volcano of Yellowstone getting ready to blow, like that is not even a sneeze compared to the Siberian traps. 1 million cubic miles of lava came out at this time. And 2 million years is not a very long time, geologically speaking. We've since looked at these Siberian traps for other times, and we can link this activity when it's happened at other times as well to other smaller extinction events. Where all this lava came from is actually likely the same mantle plume, that plume of hot rock that is now feeding into Iceland. As the continents have shifted, that is what kind of sits on top of that same mantle plume now. And for whatever reason, it was incredibly, incredibly active towards the end of the Permian, pushing out all that lava like we've never seen before. So here's from this, from a park that's up in northern Siberia here in the area of the traps. This is a kind of a geologic cut, so it's nice to see the different layers there of the igneous rock. Like I said, covered a huge area. But that's not all. When these eruptions were happening and where they were not happening at a place that was exclusively igneous in nature. They actually burst through a sedimentary basin. So an area where over time, different layers of sedimentary rock had built up. It had been accumulating organic material for hundreds of millions of years. There were shales, there were coals in layers up to 12 kilometers thick. So picture, if you will, not just lava that's covering and like filling 1 million cubic miles, but all of that lava punching through some of the biggest deposits of fossil fuels on the planet at that time. So we're getting the carbon dioxide release from the lava and the volcanism itself. We're getting the carbon dioxide release from all of these coal and other organic materials burning. And we also would have had huge explosions by this as well. So as that coal and as those layers started to burn, they would have burst through in massive explosive events, burning through most of this world's reserves of fossil fuels within a few thousand years. So it incinerated all these deposits, it exploded, then not just releasing again that carbon dioxide, but also a variety of other chemicals that would have been present in these sediments as well, like methyl chloride, like butanes, like methyl chloride as well. And all of those chemical compounds would have then destroyed the ozone layer at the time as well. So you can see we're just stacking up thing on top of thing here. We have fossil pollen evidence from this time showing deformed pollen grains and spores. So the posited theory there is that these are all UV-induced mutations that happen not just to animals, but also to plants and other organisms here now too. So this is all sounding really bad. Let's go on and make it worse. This here is some of the basalt rock found in the Siberian traps, but the shiny stuff within it is not that igneous rock. It's something else. It's actually iron. Mostly iron, about 94% iron, about 4% nickel, plus a few other impurities. So basically, as all of those coal reserves burned, they left behind the iron that would have been contained within the plant, and also would have left behind other trace minerals as well. The lava itself also contained a number of metals. Very cool, but what we're actually going to look at here is the nickel that's contained within this, which to us, nickel seems fairly inert, right? We mine it out of the ground, it doesn't really cause any harm. But let's say that in the ocean, you're a species of archaea, a type of bacteria that doesn't feed on other bacteria, doesn't feed on plants, doesn't feed on sunlight. You feed on chemical things, and you output methane. So there is a theory, which is, again, all of these are theories because we can't step back and look at the Permian in person. But this species, Methanosarcina, might have been one of the extinction drivers of the Permian. We can track back in the genetic history of this organism that this species here was able to obtain a new metabolic pathway via gene transfer from another bacteria, which is how bacteria get smarter. They pick up new genes from other bacteria that allowed these bacteria to exponentially reproduce because of the excess of nickel that was present in the ocean at this time. And because these bacteria don't output carbon dioxide, they don't output oxygen, they output as their waste product methane. And methane, while it doesn't last very long in the atmosphere, is a very, very strong greenhouse gas and a very, very strong driver then of climate change. So all of this can be read in the rocks, right? The ocean temperatures at the equator went above 40 degrees Celsius or 104 degrees Fahrenheit. The oceans were acidic. They were low oxygen with high levels of hydrogen sulfide. And this happened, again, for a number of factors because of the, move ahead here, because of the carbon dioxide that came out of the volcanoes then contributed to warming of the atmosphere. When we have increased warming and increased carbon dioxide, we have increased weathering. Weathering is the chemical breakdown of rocks that allows those nutrients present in the rocks to be available to plants. So we have more nutrients entering the oceans and the seas. That presence of the nutrients will then cause algae to grow, for example, taking up more oxygen in the water, creating areas of anoxic conditions where there is no available oxygen for plants or for other organisms. We also have that carbon dioxide in the atmosphere dropping acid rain, as well as contributing to acidification of the oceans themselves. So we see the oceans becoming more acid. Therefore, anything that has a calcium carbonate skeleton, like the corals, like the blastoids, like all of those shelled organisms, their bodies literally start to degrade because they are not able to withstand the acids that they are now living in. And then we have the sulfur aerosols and all of the ash that was produced by the volcanoes as well. So all of these acted in different time scales. We likely saw on a very short time scale as the Siberian trap started to erupt, we'd have explosive activity. We probably had wildfires. We then, though, had sulfur aerosols that blanketed the earth and cooled things down for a time, just like we saw in our lifetimes, when Pinatubo erupted, we had cold summers. But those sulfur aerosols will eventually degrade. We start to have, sunlight that hits again, and now it's going to start to warm up, and it's going to keep warming and keep warming because we have all this carbon dioxide that's been blown out not just by the Siberian traps, but also by the coal and the shale oil that's burned. It's just this compounding and compounding and compounding of conditions. And if that doesn't sound bad enough yet, we have another theory. This is unconfirmed, but makes sense in terms of the physics of it. We think that temperatures at the equator would have warmed high enough that we would have had not just regular cyclones or hurricanes, but something called a hypercane. That can really only happen when sea surface temperatures reach above about 50 degrees Celsius of around 115 Fahrenheit. If our average temperatures are 104 Fahrenheit, we probably saw, summertime conditions of these levels of 120 or so. Hypercanes are just as extreme as they sound. They can be caused by things like asteroid or comet impacts, or those supervolcano eruptions, or large eruptions of flood basalt. And the theory here is that they would have been able to form, and they would have wind speeds of over 500 miles per hour, gusting to over 600 miles per hour. Any forests still standing would have been pushed down by this. And their lifespan was tremendous. They don't just reach into the lower stratosphere, they reach all the way through the upper stratosphere and can go on for days and days and days. The pressure drop would have been just incredible. So now we have not just these winds, but because we have, dangerous ocean conditions where hydrogen sulfide is being produced, we have this carbon dioxide. what these hurricanes can then do is take conditions that might have only been present, in certain areas of the globe and spread that toxic gas around a much larger area. So you're not just contending with the winds, you're contending with all of the toxicity that's being carried by this hypercane at the same time as well. So what on earth was even able to get through this time? As we said, not much. We did have an animal that survived. We had more than one animal that survived, but this is like the guy. This is Lystrosaurus. Lystrosaurus was a survivor of the Permian extinction. They are up to 95% of the fossil vertebrates in some of the fossil beds. This is what we call extinction taxa. These are the dandelions of the world of that time, right? What lives is the stuff that can live through anything because nothing else can. And this is what goes on to then repopulate the world. So this is one of the dicynodonts, one of the therapsids that went on to eventually give rise to mammals. The mammal crew made it through, so did the sauropsids, because we're going to, as we look forward into the Triassic, we're going to see the age of reptiles start to grow. But poor Lystrosaurus here just had to feed on the very few things that were left, and like I said, was kind of feeding on the very few forests that were left, the very few plants that were left, and the whole of the planet was likely kind of not the same ecosystem, but really dominated by the same species for a very long time. It took 30 million years after this event for us to see similar levels of vertebrate biodiversity, which is a very, very, very long recovery period. So all of this sounds like things that could never happen today. Right? We had so many compounding factors that came in here. It's hard to look at this and say that this has any lessons to us today. But it really honestly does. We have many lessons to the presence. The Permian is the period that is usually held up as the closest analog for how we are treating our planet today and how we are moving through the planet today. So while there were a combination of factors that took it as far as the Permian extinctions did, we're not necessarily looking at dissimilar factors present on the planet today. While there were huge influxes of carbon into the atmosphere, we are now putting carbon into the atmosphere faster than it happened at the Permian. We don't have access to as much carbon as there was in the Permian unless we start to have some massive supervolcano explosions. If we burned everything that we could possibly burn, we would release 5,000 gigatons of carbon, which is like, that would be so incredibly catastrophic, we can't even imagine it. The Permian estimates are at least twice that, up to even as much as 8 times that. But it tells you that what we are doing is still putting that carbon in there really quickly, even faster than this period of time, which was the most destructive that we saw on Earth. Carbon dioxide in the atmosphere and global temperatures are always very closely linked. We can see it going back in direct records up to about 1 million years ago, and we can see it looking back in other records as well. They're always really closely coupled. There are certainly other factors that affect temperature as well, but carbon dioxide levels in the atmosphere, that's our planet's blanket. And if you put more blankets on, you're going to feel warmer because more heat is trapped. And we are, like, if you look at that blue line there, that is what we have very quickly added to the atmosphere. And you can imagine kind of what the catch-up would be if we don't do anything about that, and what that might look like. That ozone hole that was present in the Permian was something that we made in our lifetimes as well, right? Ozone is an odorless gas. You probably don't notice it or think about it most of the time unless you're putting on sunscreen. But chemically, ozone is like really important to life on our planet because it is an absorber of ultraviolet radiation, specifically UVB, which is one of the highest kind of carcinogenic types of UV radiation. We humans and probably most of us are aware of this, we accidentally almost killed the ozone layer by producing some really great fridges and refrigeration systems. The chemicals that the Permian accidentally produced, we produced on purpose to be able to keep our drinks cold. And one of the greatest successes of our times is that we were able to stop this so quickly and so thoroughly. And it's been now about 15 years since we've seen an increase in the ozone hole, and the ozone hole is now very much repairing itself these days. So this is what the trends have been here. So back in the mid 90s, we had big holes, and it's very much a seasonal thing. But as we move forward here, and this is today, we see that there is still, lower amounts of ozone presence over the Antarctic, but those holes are closing. It is repairing. We managed to figure that out and move forward. Another lesson to our present is the amount, it all really comes back to carbon dioxide and the carbon that we're putting out into the atmosphere, because that carbon dioxide doesn't just stay in the atmosphere, it also gets absorbed by our oceans. Carbon dioxide reacts with seawater to make it more acidic. And just like, right, if you have an acid tummy and you take Tums, Tums is calcium carbonate, and it reacts with that acid to neutralize it and to make it less acidic. So that calcium carbonate that's present on like clams and oysters and coral, they rely on pretty specific pH ranges, a pretty specific small range of pH within the ocean. And as we are making that ocean more acidic through the absorption of CO2, we are already starting to see some organisms, like those little forams, start to become pitted and develop holes because they're not able to sustain their calcium carbonate skeletons. Right. And part of this is, again, comes down to how quickly we're doing things. The ocean is an amazing buffering system, and we have a very long-term buffering system present on a planet where if you put a lot of carbon dioxide into the atmosphere, things warm up. As you warm things up, there's more rain, there's more acid in the rain, the rocks are going to break down faster, and as we weather those rocks, that actually removes carbon dioxide and locks it up as calcium carbonate and as other carbonate rocks. We're not giving the planet time to buffer in that way. So our oceans have already dropped about 0.11 pH units, and that is already enough that we're seeing changes within the organisms living in our world here. So I'm leaving us on kind of what feels like not a really happy note, but what I really wanted to bring us back to was the theme of we've seen it. We know what happens. We can look back at this and see how this can go. And we are a very adaptable species. That's why we've done so very well. And we just need to adapt a little bit more, because we actually kind of can see the outcomes of what we have going here. From ocean acidification to a lack of oxygen in the oceans to the warming temperatures, all of these things are things that we can address because we're not volcanoes. We have the ability to stop doing all these things if we decide we're going to stop it. So I apologize for going right to the end of the hour here. It was a large topic, and I'm happy to answer a few questions if there's any that Rob wants to pull up.
All right, thank you so much, Eleanor. Now, before we start in with the question and answer session, I would like to remind everyone that you can submit your questions via the question field in your GoToWebinar control panel. And if you're interested in traveling with NatHab, you can visit our website at nathab.com for trip details or call us at 800-543-8917 to speak with an adventure specialist. All right, let's get to some of these questions. So, were there significant mountain ranges at this time?
There were significant mountain ranges at this time. I'm going to scroll on back to good old Pangea here. Where are we here? So you can see those locations where our continental land masses had come together, between what's now South America and Africa and North America. There were what were called the Central Pangaean Mountains. There were also a number of fringing mountain regions along the outside of the continents, but absolutely there were mountains, and those mountains would have been like today. They would have been weathered, they would have been breaking down over time, and those mountains are not really they're not mountains anymore for the most part, but there were mountains then.
Gotcha. Thank you. So, did the extinction event take place over many years or decades, or did it come pretty quickly?
Yeah, the Permian is a time when we have differing opinions on how fast things happened. The kind of more detailed story is that there were likely a couple of smaller extinction events midway through the Permian, but the what has been posited, what has been put forward as a theory, is that the end Permian may have happened over a period of time as short as 10,000 years. 10,000 years might sound like long to you and I, but it is unbelievably quick. Like that is death and destruction every single day. Most of the time that we talk about mass extinctions, if we're talking about a fast one, we're talking about a million years. And here we're talking about tens of thousands. So there were like other events within the Permian that changed the species makeup, changed what was there, but that end Permian was very likely a very, very fast moving event.
Gotcha. Thank you. So, do we know what exactly caused the temperatures to change? Was it a combination of things?
Yeah, the temperature change would have well, it would have been exclusively from the addition of carbon dioxide into the atmosphere. And most of that carbon dioxide came directly as volcanic gas release. So when a volcano erupts, it doesn't just spew out lava, it also spews out gases. One of those gases is carbon dioxide. Um, and there's often quite a bit of it. There's also things like hydrogen sulfide that come out and other gases as well, and ash. So a lot of carbon dioxide from the volcanism, and then more carbon dioxide from burning the coal and the peat and the shale gases that were also on top of the volcano, and then more carbon dioxide again from burning all the forests. And just to be clear, like what carbon dioxide does when we release it into the atmosphere is it looks like to your eye, right? When we see the molecular formula there, you'd say, well, how is it doing anything differently? But what it does is that when the Earth gets energy from the sun, it takes it as infrared radiation, it absorbs it, the Earth warms up, but then the Earth re-emits some of that radiation. So, when you sit on a hot rock in the summer and you can feel the heat coming off the rock, that is the Earth radiating heat back at you. When we have carbon dioxide in the atmosphere, carbon dioxide will absorb that radiation of heat coming back from the Earth and then re-emit it back out into the atmosphere. So it's something that did I put a little thing in here? Sometimes I do. Oh, sorry. Sometimes I have more things that I can pull up. So here's our greenhouse effect. So, right, we have solar radiation coming from the sun, but then the infrared radiation is emitted from the Earth, and it gets trapped in the atmosphere and basically bounced around by carbon dioxide because it's always absorbing it and re-emitting it. Therefore, the more carbon dioxide you have, the more gets trapped in the atmosphere.
Great. Gotcha. All right. So let's talk about the all the landmass being on one side of the planet. Well, would that have any effect on the weather or the planet's rotation?
Yeah, the planet's rotation, I don't know. That's a really good question. Our Earth has been slowing down over time. So at the time of the dinosaurs, for example, the planetary day would have been between 22 and like in 20 hours. So it was a shorter day, but the rotation, I don't believe it had any more of a wobble than it currently does. It would just equalize out with the tides and where the water sits as it spins, but it definitely would have had an impact on how ocean circulation works. Like today, we have some really well-known currents like the Gulf Stream. The Gulf Stream takes a lot of heat from the equatorial areas and brings it north, keeps areas like the south coast of Iceland warm and the east coast of the US, and then all the way into places like Britain, warms it up because it's carrying that excess heat up. We don't know what the ocean currents were doing at the time of the Permian, but they were likely working in similar ways to take that heat that we get most of the heat towards the equator and taking that warm water up to where it's colder. That's how ocean currents set themselves up, is to move from warmer areas into colder areas and make this great big conveyor belt system. The weather on that supercontinent would have been overwhelmingly like much drier than today, especially in the middle areas. And it would have also been more seasonal. So where I live, I'm in like Manitoba, just above North Dakota. If you think North Dakota, pretty similar. We have what's called a continental climate. We're in the middle of the continent. We're not getting a lot of excess water coming our way because we're so far away from the water sources. And we have a lot of heating and then cooling. So nothing is, the water is really great at moderating temperatures, and we don't have that happening in the middle of the continent. So you have hot summers and cold winters. And throughout those hot summers and cold winters, it's very, very dry. So that is likely what we saw a lot of in Pangaea, because we just had so much continent. And it was all together. A lot of that would have been very, very seasonally extreme temperatures and precipitation.
Great. Thank you for that answer. So let me ask you, how long will it take for the ozone layer to repair itself? Do we know?
I have not looked at estimates for a little while on that, but it is still like currently in progress. I believe last time I read they were estimating like within, I think I remember reading within my lifetime. So say within the next 50 to 100 years, we would expect a near full recovery unless we manage to damage it some other way. But it slowly replenishes itself as oxygen interacts with the UV coming at it. Some of those oxygen molecules will split apart and then form O3, the ozone layer. So it is a gradual recovery, but now that we are no longer actively destroying it, it is just a matter of waiting for it to come back. So it is on its way.
Great. Good to know. So let me ask you this. Have cockroaches always been with us?
Cockroaches have not always been with us, but they've been with us since about 200 million years ago. And this is the oddity of the Permian extinctions, is that we joke a lot about, cockroaches being the only thing left. This was so bad that not even insects made it through unscathed. The cockroaches didn't make it through the cockroach ancestors were also hit by the Permian extinctions. So that just tells you how bad it really was.
Great. Thank you for that. Unfortunately, that will be the last question that we do have time for today, Eleanor. So I'd like to hand it back to you for any closing comments you may have for us.
Well, I will keep it quick here and just say thank you for everybody for coming by and learning. I know it's a hard topic and there's a lot of information here, but I think it's really important and it gives us a lot of lessons for our time today. Like I said, we're not volcanoes, we're humans with abilities to think and reason, and we have the ability to make good choices about what we're doing. So thanks everybody for learning a bit more about that.
And thank you so much for taking the time to present for us today. And I'd also like to thank everyone who tuned in today. So remember, if you are interested in information on how you could travel with NatHab, give us a call at the number on your screen, or you can also send us an email at info@nathab.com. Join us Monday for our next daily dose of nature. You can check out next week's lineup, including our registration links, on the website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I will conclude today's webinar. Goodbye, everybody. We'll see you next time.